Hello and welcome to the next lecture. Now I'm going to talk about simulation in this lecture. Simulation is a very important topic for statistics and for a number of other applications. So I just want to introduce some of the functions in R that can be useful for doing simulation. So there are a couple of functions that are available for simulating numbers or variables from given probability distributions. Probably the most important of which is the normal distribution. And so we can generate variates from the normal distribution by specifying a mean and a standard deviation for that distribution and then calling the rnorm function. So the rnorm function will simulate normal random variables from a distribution that has a given mean and a standard deviation. There are few corresponding functions in the R for the normal distribution that can be used to evaluate the probability density or to evaluate the cumulative distribution function and also for evaluating the quantile function. So another function for generating random variables is the rPois function, which generates Poisson random variables from a Poisson distribution with a given rate. And so there are a number of functions for generating random variables from the standard probability distributions, and you can use these to run simulations. So probability distribution functions, there are basically 4 functions associated with them, and so for any given distribution like the normal distribution, there will be a function that starts with the D, a function that starts with an R, a P and a Q. So there will be 4 different functions for each distribution. I have already mentioned that there's the rnorm function. The rnorm function is for random number generation. There's a dnorm function which evaluates the density of the probability distribution for given mean and standard deviation. There's the pnorm function which evaluates the cumulative distribution, and then there's the qnorm function which evaluates the quantile function. So every distribution has these 4 types of functions. So for the gamma distribution, there will be a d gamma, an r gamma, p gamma and a q gamma function. And for the Poisson distribution, there's the rPois, dPois, pPois and qPois functions. So working with the normal distribution requires these 4 functions. So I mentioned there's a dnorm, pnorm, qnorm and rnorm, and you can see they each take a number of different parameters. All the functions have required that you specify the mean and the standard deviation because that's what specifies the actual probability distribution. If you do not specify them, then the default values are a standard normal distribution which has mean 0 and standard deviation 1. For the dnorm function, you can evaluate the density, and there's an option that allows you to evaluate the log of the density. Most of the time when you evaluate the density function for a normal distribution, you are going to want to use the log of that value, but the default is false. For the pnorm function and the qnorm function, there's also an option to evaluate it on a log scale. Another option is to evaluate whether or not you want to evaluate the lower tail of the distribution. So the lower tail, if you look at the probability distribution, it's the part that goes to the left, it's the lower tail. If you want to evaluate the upper tail, sometimes you want to do this, then you want to say lower tail equals false, and that will evaluate the upper tail of the distribution. And finally for rnorm, there's only 2 parameters, mean and standard deviation and an n, which is the number of random variables that you want to generate. So if n is 100, you will get a vector of 100 numbers that are drawn from the normal distribution. So just to be more explicit, if pi is a cumulative distribution function for the standard normal distribution, then pnorm is equal to pi and qnorm is then equal to the inverse of pi. So a quick example here, if you want to generate some random variates, you can just call rnorm and pass in an integer, which is the number of variables you want to generate. So here I am passing 10, and you can see that the vector that's produced will be random normal numbers which have mean 0 and standard deviation 1. If I wanted to generate a vector that had mean 20 and standard deviation 2, I just need to specify that explicitly in my call to rnorm. So here I call the summary on this vector x, which has 10 normal random variables and their mean is roughly 20 and the standard deviation is 2. So anytime you simulate random numbers from a distribution for any purpose, it's very important that you set the seed for random number generator, and this can be done with the set.seed function. So what's important to know that on computers, when you generate random numbers, the numbers are not actually random, but they appear random, and that's the important thing. And so the idea is that if you wanted to generate the same set of random numbers again, you could if you wanted to, because the numbers are not actually random, They are what called pseudo random numbers, and so here I am setting the seed to be 1. So the seed can be any integer you want. You just pass in an integer and that's the seed. So here I am going to set seed equal to 1, and then I am going to generate 5 normal random variables. And so here I've got my 5 normal random variables. They have mean 0 and standard deviation 1. If I generate another 5, you will see that the vector is totally different because it's another random sample of 5. However, if I reset the seed to be 1 and I draw 5 again, you will see that they are exactly the same as the first 5 that I drew. So when you set the seed, it kind of sets a sequence of random variables that's just going to occur. And if you reset the seed, you kind of set the sequence to go back to where you started, and then it will continue to kind of generate random variables from there. So this is important because it allows for you to reproduce random numbers that you generate. Now that might sound strange, because why would you want to regenerate the same random numbers twice? In many applications, you do want to generate the same random numbers twice so that people can reproduce what you have done. And particular, if there are some errors or problems in what you have done, you want to be able to just kind of go back to the exact situation that produced those problems. So whenever you do a simulation, you always want to set the random number seed so that you can go back and get the same results. So I have demonstrated how to generate normal random variables, but of course you can generate random variables for other probability distributions. So the Poisson distribution, which is of course very popular, here I am generating 10 Poisson random variables with the rate of 1. And so of course Poisson data are going to be integer. Here I am generating 10 Poisson random variables at the rate of 2. So you can see they are slightly larger, and then here I am generating 10 Poisson random variables with the rate of 20. And so for the Poisson distribution, the mean is going to be equal to the rate. So you can see that roughly in each of these 3 cases, the mean is roughly equal to the rate that I specified. I could also evaluate the cumulative distribution function for the Poisson distribution. So here in this first example, I want to know what is the probability that a Poisson random variable is less than or equal to 2 if the rate is 2. And so this is the probability, it's 0.67 roughly. If I wanted to know what's the probability that a Poisson random variable with rate 2 is less than or equal to 4, you can see the probability is getting bigger. And here I can see the probability that a Poisson random variable is less than or equal to 6, and it's very close to 1. So the cumulative distribution allows you to evaluate these probabilities. Now we have talked about how to simulate random numbers from the simple probability solutions. But the question now is what if we want to simulate data from a model like a linear model? So I've got a fairly simple linear model here. It has a single predictor x, and it's going to have random noise, what I called epsilon, that has a normal distribution with standard deviation 2. There is the outcome which is going to be generated by using these two regression coefficients around intercept beta naught and a slope beta 1. And I'm going to assume that beta naught is equal to 0.5 and beta 1 is equal to 2. So the question is, how do I simulate from this model now that I have specified what it is? So here first I set the seed. It's always very important to set that seed. So I set it to be 20. I generate x, the predictor, which has a standard normal distribution. I generate epsilon, which is going to have a standard normal distribution with mean 0 and standard deviation 2. And then I'm going to add them all together after multiplying the regression coefficients to generate my y. And so for the summary here, you see that y has roughly a mean of 0.68 and it ranges from about -6 to +6. And then I can plot the data to see what it looks like. Here plot is on the next slide. So this is the plot of the x that I simulated and the y that I simulated from the linear model. And you can see that they very clearly have a linear relationship that follows the model that we specify. So just a slight variation of the previous example. What if instead of x being a normal random variable, what if x is a binary random variable? So maybe it represents gender, or maybe it's some treatment versus control or something like that. So here it's very simple. I can generate binary data from the binomial distribution using the rbinom function. So I set the seed again and I generate 100 binomial random variables, and this comes from the binomial distribution, which is n equals to 1 and p equals to half. So the probability of 1 is going to be equal to 0.5. So I generate 100 of those and then I generate my normal random variables. my normal error term, which is going to be the mean 0 and standard deviation 2, and then I combine them all together, which should produce my y. So now I look at the summary of y. I see the mean is about 1.4 and the range is about from minus 3.5 to almost 7. So now when I plot the data, of course they will look very different because the x variable is binary, but the y variable is still continuous. It's normal. So here you can see that there appears to be a pretty clear again linear trend going between from x equals to 0 and x equals to 1. Now suppose you want to simulate from a slightly more complicated model, a generalized linear model, perhaps with a Poisson distribution. And so for example, you might want to simulate some outcome data that are count variables instead of continuous variable. So we have to use a slightly more complicated approach to do this in particular, because the error distribution is not going to be normal, it's going to be a Poisson distribution. And so let's assume that the outcome y has a Poisson distribution with mean mu, and that the log of mu follows a linear model with an intercept beta naught and a slope beta 1. So x is going to be one of our predictors. So let's assume that beta naught is 0.5 and beta 1 is 0.3. So how do we simulate from this model to get our Poisson data? So we need to use the rpoise function for this. And so we first set the seed as always and we generate our predictor variable x, which is going to have a standard normal distribution. Then we are going to simulate, rather say generate our linear predictor log of mu, which is just adding the intercept and the slope coefficient times x. So that's the log of our linear predictor. But in order to get the mean for our Poisson random variable, we need to exponentiate that. So we simulate 100 of these Poisson random variables using the rpoise function, and we give it the exponential of our log mean. So when we summarize this, you will see that the mean is about 1.5 and our range is between 0 and 6. When I plot this data, you will see that they look like Poisson data, and there's clearly a linear relationship between x and y. As x increases, the count for y generally gets larger, but the data are still count variables here. So the last function I want to talk about is the sample function, and the sample function allows you to draw randomly from a specific set of objects that you specify. So if you give it a vector of numbers, it allows you to draw a random sample from that vector of numbers, and so you can kind of create any arbitrary distribution that you want by specifying a vector of objects and then sampling from it. So here for example, I am going to sample from the integers 1 to 10. So I pass the vector of integers 1 through 10 and I tell it that I want to sample randomly 4 of them without replacement. So I'm just choosing 4 random entries from 1 to 10, and here I get 3, 4, 5, 7. If I do it again, I get 3, 9, 8, 5. So in this example, I won't get repeated numbers because I'm not sampling with a replacement. I don't have to just sample numbers. I can sample letters if I wanted to. So here I'm taking the letters A through Z and I'm just going to sample 5 of them without replacement. And I just get Q, B, E, X and P. Now what happens if I don't specify anything? I just give it the vector of objects. So here I'm passing sample the vector 1 through 10, and if I don't specify anything else, what it does is it gives me a permutation of those. So here the vector 1 through 10 is just permutated in a random order. If I call it again, I get yet another permutation. So lastly, if I want to sample from 1 through 10 but with replacement, I can specify the replace equals true argument. So now I am sampling 1 through 10. I am getting a vector of 10 numbers from the vector 1 through 10, but because it's with replacement, I can get repeats. So you can see I got 8 3 times and I got 9 2 times. So that's how you sample with replacement. So that's a very quick summary of the simulation functions in R. You can draw random samples from specific probability distributions with the R functions. So R norm, R poise, R binom we saw already. All the standard distributions are going to be built in that, but probably you will need things like the normal, the Poisson and the binomial, the exponential, gamma, etc. All those functions are built in, and you can use the corresponding R functions to simulate from them. The sample function can be used to draw random samples from arbitrary vectors if you want to kind of create your own distribution here. And it's very important to remember to set the random number generated seed anytime you simulate data in R, so that you can reproduce the results that you got at a later date. Lastly, I want to mention here that if you didn't understand our linear models that we discussed here, you don't have to worry. We will cover them in our later course in more depth. So that was all on simulation in R. More material for you will be provided in the blog as always, so definitely check that out. Finally, I hope that you will find this lecture very useful, and if you do, then don't forget to like the video, share it with your friends and peers, and importantly subscribe our channel so you don't miss on latest lectures. So see you in the next lecture. Till then, ciao.